let us now use the model of the induction motor to do speed control by V by F method. So let me open the schematic. So I have made the schematic for simulation in NgSpice. So it is like this. So this is the V by F control of the induction motor. So open loop V by F control, and you could extend it for closed loop control also later, and I will show you how. Now here I have the model of the induction machine. So what is the model of the induction machine and how I have placed this here? You can always go to the components dialog, go to this model, and here you have the model of the induction machine coming in there. So that is how I have brought that in. It has the sub-circuit model. It is XIM. Note the X is the first character, and that is placed in EDT01.sub. Let us just have a look at that. You see that there are three inputs, VU, V, VY, U, V, W. It could as well be A, B, C, or R, Y, B, three phases. And there is a torque input, load torque input. This represents the load torque that is felt by the induction machine on the shaft of the machine. And there are some outputs. The three phase currents, U, V, W, which are coming as which are actually coming as outputs of voltage, zero voltage sensor being used to sense the currents. And you are also getting here the shaft speed as the output. So this is the model of the induction machine, and that if we go to the EDT01.sub, you will be able to see the model of the induction machine. This is the model of the induction machine placed here. This is a sub-circuit and it has IM. So NVU0, this is the node voltage coming from the inverter. The inverter has three midpoints, U midpoint, V midpoint, W midpoint. Then there is a torque input point, and these are outputs, sensed outputs of the currents IU, IV, and IW, and the speed. And I'm passing some parameters of the motor, which I already discussed, which we used in the octave simulation. The same motor parameters are passed here. Then in the sub-circuit, pole to neutral conversion, I'm using the B source. Go through this code, very simple. Then three phase to two phase, UVW to AB is done by again another set of B sources, programmable B source. The state equations, these are the four state equations. I'm using ISA dot, ISB dot representing IS alpha, IS beta, IR alpha, IR beta, and you have the omega m. These three equations are plugged in using the B sources, and then afterwards I am converting the alpha beta to UVW outputs, and these are the currents, voltages, which are actually representing the three-phase currents. And also I have one more output coming as representing the speed. So this is what is there in the model of the induction machine. I have separate sub-circuits for UVW to AB, that is three-phase ABC to alpha beta to ABC or AB to UVW, alpha beta to DQ, AB to DQ, DQ to alpha beta or DQ to AB. So this is what I'm the polar to rectangle, and for V by F lookup table. This is the model of a lookup table. The remaining PID, all these things we have seen. So this is what is there in the sub-circuit file, and I will close that, go back to this one. So this is the model of the induction machine. This is the source. I'm giving an arbitrary piecewise linear source. If you come to this portion of the circuit here, the control portion, it is not in closed loop, but I am setting it up such that even for closed loop with minor modification you should be able to do. I will tell you how to do that later, but first for the open loop simulation. So here this is the reference for omega m, where it is going from -100, and then after a period of 20 seconds it goes to +100 and then remains at +100. So it goes from -100 to +100 and then remains at 100. So that is the reference shaft speed that we are trying to give, and it is in radians per second. Now this goes through this block. This is a summer block, and to that is added subtracted 0. So it goes through as omega mechanical. This is a PID controller, but if you see within the PID controller, Ki is 0, Kp is 1 and Kd is 0, which means it is again a pass through. So this is just a pass through element now, right now, and at A you will get a value same as omega mechanical. And then here again I have an adder where the other input is 0. So this again is a pass through. So what you get here is the same value Vref omega mech, which is available here as the node voltage. The same thing is going to appear here at the input of this lookup table. Now if that is considered as omega synchronous speed, then using the lookup table which we saw in the EDT01 as the sub-circuit, you will get as output the voltage which is proportional to omega. So this is where the V by F lookup table comes into the picture. So you have Vs and also omega coming in here, and this is a vector, Vs vector, and omega is the frequency at which it is rotating, or omega t is the angle. So this polar coordinate system is converted to a rectangular coordinate system. Again, this is a sub-circuit, x polar to rectangle. We saw that polar to rectangle sub-circuit is available in the EDT01.sub, and this block converts polar to rectangle alpha beta. So alpha beta or AB is used as input to this block, where you have AB to UVW or alpha beta to ABC, and converts it into three-phase quantity. And this three-phase voltage quantity is given to the induction motor as the input, and based on that the currents and the torques are developed, and the motor will run and be speed controlled based on the V by F action. So this aspect we will simulate. This is open loop V by F. If you want to do closed loop V by F, now this is where these 2 points you need to do something. So what is it that you have to do? You have to give, instead of 0 here, grounding here, you give n omega m, you give the omega m as feedback. Give omega m as feedback at this point. So that will be the feedback. There will be an error, and PID give both Ki and Kp, appropriately tune it such that PID will do the controller job, and error here will go to 0, which means the feedback omega will be same as this reference, and the reference will now represent the mechanical speed. And the output of the PID at node A, you will get the slip frequency. To that you add here again omega m. Here you have to add omega m. So added, you will get here the synchronous frequency, and then all other operation is same as in the open loop. So this portion here can be used for converting it into a closed loop operation. Only change that you need to do is to both these grounded points give n omega m. Give this omega m as the node point here. So this will see to it that it will go into a closed loop control, V by F control. and also simultaneously you need to tune the PID accordingly such that the error at the input of the PID is 0. Then you will get V by F closed loop control action. I will leave this V by F closed loop control operation of the induction motor as an exercise to you. Try it, understand it, try it, and then see how it operates. I will now go through the open loop operation of V by F control. So let us now open let us now go and open the command window. At the same time, I also would like to have a look at the circuit file. So if you go and look at the circuit file, you will see that it is very similar to what we have been doing. It is for 60 seconds. It uses the V by F netlist which will get generated, and as usual the background is white, the foreground is black, and we are seeing the reference omega m, the I. This omega m is the actual shaft speed coming out of the model of the induction motor. This is one phase current, U phase current, and the torque, load torque, which is scaled. So let us run the simulation. I will execute the simulation. So first what will be done is I'll give run sim v underscore by underscore f. So this will generate a netlist and then run the simulation, execute the simulation for 60 seconds time, and this is the waveforms that you see. So you see that this red waveform minus 100 to plus 100 is the reference waveform, continues to stay, and the blue is the actual speed waveform of the induction motor coming out of the induction motor model for the specific kind of torque, load torque input. So you see that the reference red is here, and the blue waveform is following the reference waveform and reaching steady state here. And at this point, you are having a torque disturbance, having a torque pulse of 100 Newton meters scaled, and you will see that the speed is falling down, and then when the torque pulse is released, goes back, you will see that the speed is again trying to go back to the steady state value. And here in yellow you are seeing that there is the U phase current. Let me zoom this up and you will see that this is the U phase current, and as the speed is crossing 0, you will see that U phase current which is changing phase and crossing over to 180 degrees phase. So this is in the negative zone when the speed is negative, and here you have the phase change and it goes to 180 degrees change in phase, and this is the positive, omega positive. So phase sequence of the three-phase waveforms will change from negative to positive. In order to see the three-phase currents, you can plot the currents which are being outputted by the induction motor model, the U phase, V phase, and the W phase currents. So if you plot that, you will see that all the three-phase currents are being seen here. So you see that this portion here, this is where you will see the speed, the shaft speed transiting from minus to plus, and you will see that the three-phase waveforms will change sequence, rotating from clockwise to anti-clockwise in this zone. So after it has crossed and become positive. So this is what would happen. If I expand this, you will see that before the phase change, the sequence is red yellow, blue. The sequence is red, yellow, blue, red, yellow, blue. And then after speed has gone positive, it is red, blue, yellow, red, blue, yellow. So on it will go. So that is how the sequence change comes into the picture and changes the direction or rotation of the space vector from clockwise to anti-clockwise. And here you can probably expand it at this point and probably see the nature of the three-phase waveform. So I will leave it to you to explore the various currents and voltages of this V by F control, and also I will recommend that you try to do the closed loop going to the schematic. At this point give omega m, at this point give the omega m feedback and both these points, and tune PID and try to execute the closed loop V by F control.